July 3, 1969, 0518 hours. Vasily Mishin stands in a concrete bunker 2 kilometers from Launch Complex 110, watching through periscope optics as 30 NK-15 engines ignite beneath the N-15L rocket. The machine is taller than a football field is long, burning 15 tons of kerosene and liquid oxygen every second. No test stand on Earth can hold all 30 engines at once, so every launch is the first full-duration systems test. This is the Soviet Union's 4th attempt to reach the moon. The first 3 ended in catastrophic failure. 30 engines fire in a 2-second ripple, and the N-1 begins to rise. Mishin knows that a single engine failure will cascade through 29 neighbors with no way to predict the destruction pattern. The race to the moon will be decided in the next 2 minutes. Vasily Mishin is chief designer at OKB-1, the Soviet bureau responsible for human spaceflight. He inherited the N-1 program from Sergei Korolev, who died in 1966 before seeing a single launch. 3 previous N-1 rockets have failed, the first in 1969, seconds after liftoff, the second later that year in the largest non-nuclear explosion in history, the third in 1971. Each failure destroyed months of work and millions of rubles. Today's launch, N-15L, carries updated engines and a redesigned chord control system. Mishin has no margin for error. Apollo 11 is scheduled to launch in 13 days, and the Kremlin demands a Soviet victory. The N-1 stands 105 meters tall, comparable in height to the Saturn V. Its first stage holds roughly 2,400 to 2,750 tons of propellant. Sources differ, but the consensus is closer to 2,700 tons. Liquid oxygen and RP-1 kerosene. 30 NK-15 engines are arranged in 2 concentric rings, 24 in the outer circle, 6 in the inner. Together they produce 4,500 metric tons of thrust, enough to lift the entire stack and send a payload toward the moon. Each engine burns for roughly 2 minutes if everything works. The NK-15 is a sound design, simple, reliable in isolation, but no one has ever fired all 30 together on the ground. The United States tests every Saturn V F1 engine individually at Rocketdyne's West Palm Beach facility, running each one for minutes at full thrust before approving it for flight. The Soviet Union has no test stand large enough to fire 30 engines simultaneously. Building one would take years, and resources the program does not have. Instead, each N-1 launch is a full-scale systems test. Engineers run single-engine tests at the factory, checking chamber pressure and turbopump speed, but the acoustic environment inside a 30-engine cluster, shock waves, vibration coupling, combustion instability, cannot be replicated on a single stand. That unknown environment will be tested for the first time at liftoff. Propellant loading completes at 0400 hours. Liquid oxygen and kerosene flow through insulated lines into the first stage tanks, chilling the aluminum structure to minus 180 degrees Celsius. The pad crew, 12 engineers and technicians, withdraws to bunker N-1-5L, 2 kilometers west of the complex. At T-minus 20 seconds, the automated ignition sequence begins. Human control ends here. The chord system, a computer monitoring engine health and thrust balance, takes over. Mishin and his team can watch, but cannot intervene. All 30 engines must ignite, reach full thrust, and burn together for 120 seconds to place the rocket on the correct trajectory. Any failure will be managed by chord, not by human decision. CHORD stands for Engine Operation Monitoring System. It monitors vibration, chamber pressure, and turbopump speed across all 30 engines in real time. If one engine fails, CHORD shuts down its opposite side counterpart to preserve thrust symmetry. In theory, the N-1 can lose 2 engines and still reach orbit. In practice, 30 engines mean 30 single points of failure. Each turbopump, combustion chamber, and fuel line must survive the full burn or trigger a cascade. The system is elegant in principle, but fragile in execution. CHORD cannot predict which engine will fail, only react after the failure begins. By then, the physics of 30 burning engines may already be out of control. The American Saturn V uses 5 F1 engines on its first stage. Each engine is tested individually for minutes at Rocketdyne before flight approval. 5 engines mean 5 potential failures, and the rocket can lose one and still reach orbit. The N-1 has 30 engines because Soviet metallurgy in the 1960s could not produce a single engine as powerful as the F-1. Clustering smaller engines was the only path to equivalent thrust. But 30 engines mean 30 turbopumps, 30 combustion chambers, 30 fuel lines, each a potential failure point. The math is unforgiving. If each engine has a 98% reliability over a 2-minute burn, the probability that all 30 survive is roughly 55%. Every launch is a coin flip. 30 engines firing in a tight cluster create an acoustic environment unlike any single-engine test. Shock waves from each combustion chamber reflect off neighboring engine bells, causing pressure oscillations that can shatter turbopump bearings or rupture fuel lines. This is called combustion instability, and in 1969, Soviet computers lacked the power to simulate the coupled vibrations. Engineers know the problem exists. They have seen it in smaller clusters, but they cannot predict which engine will fail first or how the cascade will propagate. The only way to measure the acoustic environment is to light all 30 engines and see what breaks. Every launch is an experiment with no control group. The Kremlin has demanded a successful N-1 launch before Apollo 11 reaches the moon. Leonid Brezhnev wants a propaganda victory to counter American achievements in space. Mishin has no time to redesign the engine cluster, build a test stand, or conduct incremental testing. The program is hemorrhaging money, and every failure erodes political support. If N-1-5L fails, the program may be canceled. If it succeeds, the Soviet Union can claim it was first to build a moon rocket, even if it never lands a cosmonaut. The deadline compresses every decision. Engineers flag concerns about combustion instability, but there is no schedule margin to address them. Launch is the only option. Engineers at OKB-1 refer to the 30-engine cluster as a known unknown. They know that combustion instability exists. They know that a single turbopump failure can trigger a cascade. They know that Chord's shutdown logic may not be fast enough to preserve symmetry if multiple engines fail in rapid succession. But they cannot quantify the risk or predict the failure mode. The N-1 is too complex for deterministic analysis and too expensive for statistical testing. The only data comes from flight, and every flight so far has ended in catastrophe. Mishin reviews the telemetry from the previous 3 launches, searching for patterns. But the failures are different every time. The machine is consistent only in its unpredictability. 0518 hours. The automated sequence reaches T-0. All 30 NK-15 engines ignite in a 2-second ripple, starting with the 6 inner engines, then the 24 outer ring. The sound is a continuous roar, audible in the bunker 2 kilometers away, despite concrete walls 3 feet thick. Thrust builds to 4,500 tons. At T plus 1.2 seconds, hold-down clamps release and the N-1-5L begins to rise. Mishin watches through the periscope as the rocket clears the tower, climbing slowly at first, accelerating as it burns off propellant mass. Dawn light catches the exhaust plume, turning it orange and white. For the first 12 seconds, telemetry shows all green. The bunker's telemetry consoles display real-time data from all 30 engines. Chamber pressure, turbopump speed, exhaust gas temperature, all within nominal limits. The Chord system shows 30 green channels. The rocket climbs past 200 meters altitude, velocity increasing through 40 meters per second. Engineers watch the screens in silence. 12 seconds is longer than the first launch survived. It is longer than most ground tests of clustered engines. For a brief moment, the machine appears to be working. Then, at T plus 12 seconds and 300 meters altitude, engine number 8's oxidizer pump speed drops to 0 in less than half a second. The telemetry channel turns red. The cascade begins. Post-flight analysis, what little survives, will suggest that a metal fragment, likely a turbine blade or pump seal, broke loose inside engine 8 and entered the oxidizer pump. The fragment is small, perhaps the size of a coin, but at turbopump speeds exceeding 20,000 revolutions per minute, it strikes the impeller like a bullet. The impeller shatters. Liquid oxygen flow to engine 8 drops to 0 in 0.4 seconds. Combustion ceases. The engine bell goes dark. Cord detects the failure and commands engine 15, the opposite side counterpart in the outer ring, to shut down for thrust symmetry. But the cascade has already begun. Engine 8's fuel line is still pressurized, and with no oxidizer flow to cool the chamber, the metal begins to heat. Cord's logic is simple. If an engine fails, shut down its opposite side partner to keep thrust balanced. The command travels from the computer to engine 15's propellant valves in milliseconds. Engine 15 shuts down cleanly. The rocket now has 28 functioning engines and 2 dark bells. In theory, it can still reach orbit. But Cord cannot see what is happening inside engine 8's fuel manifold. Liquid oxygen is backflowing through the dead pump, mixing with kerosene vapor from the adjacent engine 7. The mixture is hypergolic. It ignites on contact. A small fire starts in the aft compartment, invisible to telemetry, spreading along the aluminum skin that separates the engines from the main propellant tanks. When engine 8's oxidizer pump fails, liquid oxygen has nowhere to go. The feed line is pressurized at 6 atmospheres, and the flow reverses, pushing LOX back through the pump and into the common manifold shared with engine 7. Kerosene vapor from engine 7's combustion chamber leaks into the same manifold through a cracked seal. Liquid oxygen and kerosene are hypergolic in vapor form. They ignite without a spark. The fire starts as a small flame inside the manifold, then spreads along the aluminum skin of the aft compartment. Aluminum burns at 660 degrees Celsius. The fire reaches that temperature in seconds, and the skin begins to melt, exposing the base of the first stage liquid oxygen tank. The aluminum skin that separates the engine compartment from the propellant tanks is only a few millimeters thick, designed to minimize weight. The fire burns through in seconds, exposing the base of the liquid oxygen tank. That tank holds approximately 1,700 tons of LOX at minus 183 degrees Celsius, pressurized to 2 atmospheres. The tank wall is strong enough to contain internal pressure, but not designed to resist external heating. The fire heats the tank wall, and the metal begins to weaken. Meanwhile, the rocket is still climbing, now 400 meters altitude and 50 meters per second velocity, and aerodynamic pressure is increasing. The combination of internal pressure, external heating, and aerodynamic stress creates a bending moment the structure cannot survive. Aerodynamic pressure at 400 meters altitude and 50 meters per second imposes a bending moment on the weakened aft section. The fire has melted structural supports that normally distribute stress across the frame. The aft compartment buckles and the entire rocket tilts 15 degrees off vertical. The tilt sloshes propellant inside the tanks, shifting the center of mass forward and amplifying the bending moment. The Cord system, still trying to manage thrust symmetry, cannot correct for structural failure. It was designed to compensate for engine loss, not for the rocket breaking apart. The remaining 28 engines continue to fire, but they are now pushing a machine that is no longer mechanically sound. At T plus 23 seconds, the liquid oxygen tank ruptures. The weakened wall, heated by fire and stressed by the tilt, fails catastrophically. 1,700 tons of liquid oxygen vaporizes instantly as it escapes the pressurized tank and contacts the 660-degree aluminum skin. The kerosene tank, directly above, ruptures a fraction of a second later, releasing roughly 1,000 tons of RP1. The two propellants mix in open air. At this altitude, there is still enough atmospheric oxygen to sustain combustion. The mixture ignites. The rocket is now 50 meters above Launch Complex 110, tilted 30 degrees off vertical and descending. The fireball that follows will be visible from 40 kilometers away. The fireball expands to 600 meters in diameter in 2 seconds, releasing energy equivalent to roughly 7 kilotons of TNT. The shockwave radiates outward at supersonic speed, compressing the air and heating it to thousands of degrees. The rocket disintegrates instantly. Engines, fuel lines, guidance systems, all vaporized or shattered into fragments. The fireball rises as hot gas expands, then collapses back toward the ground as cooler air rushes in. Burning wreckage rains down across Launch Complex 110. The largest pieces, engine bells, turbopump housings, fall within 500 meters of the pad. Smaller fragments scatter across 2 miles. The heat pulse ignites brush fires across the steppe. The entire event, from tank rupture to ground impact, takes less than 10 seconds. 2 kilometers away, the bunker shakes. The shockwave arrives as a low-frequency thump that rattles the concrete walls and throws dust from the ceiling. Mishin is still watching through the periscope when the optics go white, then black, as smoke engulfs the pad. The pressure wave travels through the ventilation ducts, and the interior temperature spikes 15 degrees Celsius in seconds. Engineers brace against consoles. No one speaks. The building was designed to survive a direct rocket impact, and it holds. But the heat pulse is enough to blister paint on the interior walls. When the shaking stops, the only sound is the ventilation system struggling to clear smoke from the intake filters. The pad crew, 12 engineers and technicians, rode out the explosion in bunker N1-5L. They felt the heat pulse through the ventilation ducts and heard the shockwave as a deep rumble that seemed to last minutes but was over in seconds. When emergency lighting comes on, they check for injuries. No one is hurt. The bunker's 3-foot-thick concrete walls absorb the shockwave and the interior blast doors held. But the air smells of burned propellant and scorched metal. They wait for the all-clear signal from Mission Control before attempting to exit. The radio crackles. Stand by for damage assessment. Do not approach the pad until air quality is confirmed safe. The bunker goes silent again. When the smoke clears, reconnaissance teams approach Launch Complex 110, wearing protective gear and carrying radiation detectors. Not because the N1 carried nuclear material, but because the heat was intense enough to fuse sand into glass, and no one is certain what materials vaporized. The pad structure has disappeared. The steel gantry, propellant lines, hold-down clamps, all vaporized or melted. Concrete is scorched black and cracked 3 feet deep. In some areas, the concrete has melted into a glassy surface. Wreckage is scattered across 2 miles. Twisted engine bells, shattered turbopumps, shredded fuel tanks. The largest intact piece is a section of the outer ring frame, half the size of a car. Launch Complex 110 is unusable. At 0620 hours, Mishin sends the first radio transmission to Moscow. The message is brief. N1-5L lost at T+23 seconds. Launch Complex 110 destroyed. No casualties. Preliminary assessment indicates engine failure in the first stage, followed by structural breakup and propellant detonation. Pad reconstruction will require a minimum of 18 months. Apollo 11 launches in 13 days. The transmission is received in silence. There is no immediate reply from the Kremlin. Mishin knows what the silence means. The moon race is over. The Soviet Union will not reach the moon first, and there is no point in reaching it second. The N1 program will continue on paper, but without political backing, it is already dead. Within 72 hours, KGB officers confiscate all film, telemetry tapes, and written logs from Baikonur Cosmodrome. Every photograph of the explosion, every strip chart recording, every handwritten note from the bunker is collected and classified. Engineers and technicians are interviewed individually and reminded of their secrecy oaths under Article 64 of the Soviet Criminal Code. Divulging state secrets carries a penalty of 10 to 15 years in a labor camp. Foreign press receives no information. Western intelligence satellites detect the explosion from infrared signatures, but without ground confirmation, they cannot assess what failed or why. the Soviet Union issues no official statement. As far as the world knows, nothing happened at Baikonur on July 3, 1969. NASA mission planners prepare Apollo 11 for launch on July 16th, unaware that the Soviet moon program is effectively over. U.S. intelligence has detected N-1 launch activity and knows the Soviets are building a heavy-lift rocket, but they have no confirmation of the 4 failures. CIA analysts review satellite imagery showing construction at Baikonur, but cannot determine whether the pad damage is from an explosion or routine refurbishment. Without ground truth, NASA assumes the Soviets are still capable of a moon landing and proceeds with an accelerated Apollo schedule. Congressional pressure to beat the Soviets drives mission planning. The race is real to the Americans, even though their opponent has already quit the field. The N-1 program continues with diminishing political support. Launch Complex 110 is rebuilt by 1971, and 3 more launch attempts are authorized. The 6th N-1, designated N-1-6L, launches in June 1971 and fails at 51 seconds when a roll control engine explodes. The 7th and final launch, N-1-7L, occurs in November 1972. It fails at 107 seconds, the longest any N-1 has flown, when combustion instability in the first stage triggers a cascading engine shutdown. The rocket breaks apart at 7 kilometers altitude. In 1974, the Soviet government cancels the N-1 program. All remaining hardware is ordered destroyed. Launch Complex 110 is dismantled. The existence of the N-1 remains classified until 1989. In 1989, during the Glasnost period under Mikhail Gorbachev, the Soviet Union declassifies the N-1 program. Western journalists and aerospace historians are granted access to Baikonur and shown wreckage stored in warehouses. Photographs of the explosions, long hidden, are published for the first time. Engineers who worked on the program, now retired, give interviews describing the 30-engine architecture and the test stand problem. The world learns that the moon race was decided not by superior American engineering alone, but by a Soviet logistical impossibility compounded by a cover-up so complete that NASA spent years racing a competitor who had already lost. The N-1 becomes a case study in aerospace engineering programs worldwide. The 30-engine architecture is analyzed in textbooks as a violation of basic systems reliability principles. Too many single points of failure, too many coupled failure modes, and no way to test the integrated system before flight. The lesson is simple. Complexity must be validated before it is flown. Modern launch systems, from SpaceX's Falcon Heavy to NASA's Space Launch System, use clustered engines, but only after exhaustive integrated testing on the ground. The N-1's failure demonstrated that political deadlines cannot override engineering fundamentals. Competence under pressure is not enough if the system is untestable. In the 1990s, Russian engineers recover NK-15 engines from storage and sell them to the American company Aerojet. The engines are refurbished and flown on the Antares rocket, which launches cargo to the International Space Station. The NK-15, now called the AJ-26, performs reliably in single-engine and small cluster configurations. The irony is unavoidable. The engines were sound. It was the 30-engine system, untested, politically rushed, and impossible to validate on the ground, that failed. The N-1's destruction was not a failure of propulsion engineering. It was a failure of systems integration and the belief that complexity could be managed without empirical testing. NASA's accelerated Apollo schedule carried risks that engineers flagged internally. The Apollo 1 fire in 1967, which killed 3 astronauts, was partly a consequence of schedule pressure and insufficient testing. Congressional and public pressure to beat the Soviets drove mission timelines that left little margin for iteration. If U.S. intelligence had known the N-1 program was failing, NASA might have adopted a slower, safer pace. The secrecy that protected Soviet prestige also imposed invisible costs on the Americans. The moon race was won not just by Apollo's success, but by the Soviet Union's ability to hide its failures so completely that NASA never knew the the race was already over. The July 1969 N1-5L detonation remains the largest non-nuclear explosion in the history of rocketry. 7 kilotons of energy, 2,700 tons of propellant, and a fireball visible from 40 kilometers. The event was not an accident in the traditional sense. It was the inevitable outcome of a system designed without the infrastructure to validate it. 30 engines that could not be tested together, a political deadline that left no time for iteration, and a cover-up so effective that the explosion was invisible to the world for 2 decades. The N1 was not destroyed by a single metal fragment. It was destroyed by the belief that complexity and secrecy could substitute for testing and transparency. Today, fragments of N1 rockets are displayed in museums across Russia and the United States. Launch Complex 110 at Baikonur was rebuilt in the 1980s and is now used for Proton launches. The 30-engine problem has never been repeated. Modern launch systems rely on fewer, larger engines with extensive ground testing before flight. The N1 remains a symbol of what happens when political ambition outpaces engineering capability, and when secrecy prevents learning from failure. The Soviet Union built the largest rocket in history 4 times. It exploded 4 times. And for 20 years, the world did not know. That invisibility, more than the explosions themselves, defined the moon race and the Cold War space program that fought it.